Hi everybody, this is Mrs. T. This is going to be Mrs. T's Chem Talk for EP Chem on galvanic cells and their cell potential. We'll also go a little bit over the basics of galvanic cells in this video. So for those of you who don't know who I am, I'm Mrs. T. I am a chemistry teacher at Sanford H. Calhoun High School in Merrick, New York. So first of all, if you took Regents Chem last year, when you talked about Voltaic cells, we're now just going to call them galvanic cells. So whatever information you have that you learned last year about voltaic cells will apply to galvanic cells. We just give it a new name for some reason in the AP curriculum. When we talk about these galvanic or voltaic cells, they always are going to generate a voltage. They're going to generate electricity when first connected. That means that they have a positive value for E cell, and they also would have a negative delta H because they're exothermic. The electricity is the energy, the electrical energy is the type of energy that they release. They are powered by thermodynamically favored reactions. These would also be known sometimes as spontaneous reactions. The same number of electrons must be lost and gained in the two half reactions because of the law of conservation. We can use the memory tool ANOX to tell us that the anode is always the site of oxidation. Big red cat for the fact that cathode is always where reduction happens, and if it's a piece of metal, the cathode will get larger. And we know that a galvanic or voltaic cell will reach a voltage of 0 at equilibrium. Our table of standard reduction potentials should be handy when we're working on a redox question, and it lists the standard E values associated with reduction half reactions only. For oxidation half reactions, reversing the one on the table changes the sign for the value given. So if we need to reverse the reaction, we need to change the sign. This reduction potential is an intensive property, so we never multiply it by a coefficient, even if we have to do that to balance the overall net ionic equation. And on the table, if fluorine is at the top and lithium is at the bottom, that would mean since fluorine is most likely to be reduced, since fluorine is most likely to be reduced, whoever is closest to fluorine on the table is more likely to be reduced, and whatever substances or species. So if we look at a basic setup for a galvanic or voltaic cell, we usually have two pieces of metal connected by a wire. The metals are usually immersed in an electrolyte solution that has a common ion to the metal. So here aluminum is in aluminum nitrate solution, zinc is in zinc nitrate solution. So this zinc in the zinc nitrate really provides zinc plus 2 ions and NO3 minus ions. The aluminum nitrate solution provides Al plus 3 ions and NO3 minus ions in the solution. Ions will travel through the salt bridge to keep the two solutions electrically neutral, and electrons will travel through the wire and through the voltmeter from whoever is determined to be the anode to whoever is determined to be the cathode. When we look at these two elements or these two species on the table of reduction potentials, we have zinc, this is sort of the bottom portion of the table here, and aluminum here. Since zinc is higher up on the table, closer to where fluorine was at the top of this table and lithium was at the bottom, so zinc is going to be the one that is more easily reduced. That means that zinc will be our cathode. Aluminum, being closer to the bottom of the table, closer to lithium, will be the species that is most easily oxidized of the two, and that means that aluminum will be our anode for this reaction. We can also tell because remember that for oxidation we have to reverse the sign, so this would stay as a negative 0.76 volts because we're keeping zinc as a reduction reaction. For aluminum, we will have to negate the negative 1.66 volts, and that will give us a positive 1.66 volts. Putting these two together gives us the overall cell potential, and reversing this one is the way that we keep the sum positive. If we look at the cell again. So again, this is the information that we got from the table of reduction potentials. We said that we were going to keep zinc as our cathode and make aluminum the anode. So zinc's reaction stays in the same direction as it was on the table of reduction potentials. Aluminum's reaction switches order. Reactants become products and products become reactants, which is why we negate the sign of the cell potential for aluminum. Because aluminum is the anode, that means that electrons travel through the wire from aluminum over towards zinc. The zinc ions that are in solution join on to those electrons on the surface of the metal. The aluminum atoms that are part of the metal, right, that's a reactant, turn into more aluminum ions as they lose their electrons, and that creates a disturbance in the neutrality, right? The solutions are no longer neutral. That's why ions have to flow through the wire. I'm sorry, why ions have to flow through the salt bridge. Sorry about that. Ions never flow through the wire. Electrons flow through the wire. As we move, if we want to have this reaction into put this reaction into a net ionic equation, we have to balance the electrons. And if we look over here, this reaction has 2 electrons. This one only has 3. So we are going to multiply these reactions by integers. And when we multiply them by integers, we multiply the zinc reaction by 3 to get a total number of moles of electrons of 6. We multiply the aluminum reaction by 2 to make the total number of moles of electrons go to 6. Once we do that, we put the reactants and products together, but the 6 moles of electrons on each side of the arrow will cancel out, right? 2 times 3 and 3 times 2, giving us 3Zn plus 2 plus 2Al yields 3Zn0 plus 2Al plus 3. So this would be our overall net ionic equation for this galvanic or voltaic cell. If we move on, we take those pieces of information and put them back on here. And we now want to find our cell potential. So we said that this reaction for zinc was kept in the same order that it was already in on the table of reduction potentials. So we keep the sign of its voltage. But for the aluminum, we reverse the reaction. So we have to negate the sign. Sorry about that. So we have to negate the sign for that one. But notice I never use these coefficients when dealing with the voltage for the overall E cell. So even though the net ionic equation had these species multiplied, or this half reaction multiplied by 3 and this half reaction multiplied by 2, we are going to ignore any integers that you multiply by, even though we had to multiply them to get the equation balanced. We want to completely ignore these numbers that you multiplied by to balance the overall equation, and we're just going to add the resulting cell potentials together. So what that's going to look like, we're going to take the negative 0.76 from the zinc and the positive 1.66 from the, that was supposed to be a negative 1.66. So that's a positive 1.66 for the aluminum. And when we add them together, we get our overall cell potential of 0.90 volts. Sorry about that. We get the overall cell potential of 0.90 volts. So when we first connect this, our voltmeter would read 0.90 volts. And eventually the voltage would decrease and decrease as we reach equilibrium, and eventually at equilibrium the voltage would read 0. But again, you take the 2 voltages from the table of reduction potentials, negate the one for oxidation, keep the sign for the one for reduction, ignore the coefficients from the balancing of the equation, and simply add the 2 voltages together to get the overall cell potential. So hopefully this was a helpful video for you. And if you need any more help, you can certainly feel free to come in, stop in for extra help, send me an email, respond to a remind. And if you're not one of my students, hopefully this was helpful to you as well. All right, good luck with redox.